So it's 11:40. I know lots of the class isn't here yet, but so they can watch the video if they want to figure out what happened in the first bit. So I put up a poll on Piazza asking sort of how much time everybody's spending on the homework. So I was getting a lot of comments saying that, you know, I didn't have enough time to finish it. I was having a hard time with it. So please go on and answer that. I'll use the responses to kind of adjust the difficulty of the homework in the future. All right? So let's talk about last week's problem. Last week's problem was called memory management. And it's a very practical problem. And the way it works is you've got 30,000 blocks of memory set aside, each of which are tagged with a number from 1 to 30,000. And there are two operations we want to perform. We want to allocate blocks, so they all start out free, available. And when we allocate a block, we want to grab the lowest index block and use that for whatever we're going to use it for at any particular time. And then the other thing we can do is we can access an already allocated block. So that means we take a block that's been allocated, we go in and we use it for something, and then we keep it. And so after 600 seconds, after whenever the last time each block was accessed, it gets expired and it moves from the allocated blocks back into the free blocks so it can be used again. Okay? And so the idea is you have an input stream of access and allocation commands that are being fed in as standard input, and you have to write out sort of what you're expecting to happen in the memory. Okay? So the first question I asked was, assuming that we have one function that's called, we'll call one function allocate, and that takes some input and it passes some output. And then we have another function called access that takes some input and gives some output. What inputs do we want to this function? What inputs do we want to this function? And what should they return in order to print out what we want from the problem? And so for allocate, all we have as input is the time of the request. That's all we need to be able to decide what we want. And what we output is some block ID. And then we've got a bunch of code in the middle to actually do everything. So I just wanted sort of the framework for each function. And then for access, we have the block ID that we actually want to get. And then we have the time of the request. And then it's going to return a Boolean that says, did we succeed on this request? Was that block available for us to tag it or not? Okay, so that's what I wanted for in part A. And then in part B, I said, okay, I gave you a hint. I said, we're going to use two different data structures. We're going to use one that has all of the free blocks and one that has all of the allocated blocks. So we'll have all of the free blocks over here, all of the allocated blocks over here. And so the first question was, when are we moving blocks from free to allocated, and which one are we moving? And so those are going to be moved on calls to allocate. We're doing that move. And the one we are moving is the lowest ID free block. Okay? So every time we call allocate, we move a block from free to allocated, and the one that we move is whatever has the lowest ID. And then part C said, okay, now what about the other way? When are we moving blocks from allocated back into free? And we're going to do that every time we do either of these calls. So on either calls to allocate or access, before we do anything else, we're going to need to free any blocks that have expired. So if we're at time 700, any blocks that were allocated before time 100 are expired, and they need to be put back into the free queue. So expired blocks get freed. All right? A couple of people, I don't think, understood what I meant when I asked which blocks are getting moved and told me that the freed blocks are getting moved to the allocated and the allocated blocks are being moved to the freed. This is what I meant, is sort of specific. This particular block is going to get moved. These expired blocks are going to get moved. Okay? And then, once we've sort of walked through what these structures are going to be used for, I asked, how should we organize these data structures? What structures that I talked about in class are going to be useful for you? So the answer I expected was to use a priority queue for both. And for the free, what we want to move is the lowest ID. So we're going to key on block ID. And that guarantees that whatever block is free that has the lowest ID is going to be at the root, and we can pull that off very easily in logarithmic time. And for the allocated blocks, we're going to key on expiration time, so that blocks that are oldest are going to be at the top of the heap, and we can pull them off quickly. So a couple of people tried to use a fixed array or a stack for this. And the problem with that is you can get that to work. You can get the correct answer that way. But the problem is that then finding the lowest ID of a free block in a fixed list takes time proportional to the total number of free blocks. And so that means that those allocate requests will get very slow, as opposed to with a heap where they'll be much faster. Okay? One person correctly noticed that rather than using a priority queue here, you can actually use a straight queue instead to do these calls, because we're inserting blocks into the allocated queue in order of when they get called. And so if you use a queue instead of a priority queue, you can do those calls in constant time instead of logarithmic time. So that's actually an improvement over the answer that I gave. OK, so those are the structures we're going to use. I'm not going to go into the queue right now. We're going to talk about the priority queues. OK, so given a basic priority queue for both of these, we can go ahead and write a basic algorithm that can handle allocate requests. We can't handle access requests, but we can handle allocate requests. And so the idea is, every time we call allocate, first, we're going to release any blocks that are expired from the priority queue. So we'll look at the top of the allocated queue, see if that time is expired based on the time that we give our allocate request. If it is, we take it off of this queue and push it back onto this queue. And we keep doing that until we don't have any expired blocks in the allocated queue. At that point, then we go onto the free queue and take the lowest ID block that's available there, push it back onto the allocated queue with the appropriate time. OK? And if you implemented that correctly, you should have been able to solve the sample input that I gave you that only had these allocation requests. OK? So that was the end of what I asked you to do. A couple people went ahead and did the optional part, which is what you needed to be able to solve this on the online judge. So for the online judge, we also need to be able to handle these access requests. And to do an access request, we're going to need to be able to access elements in this allocated queue, not by expiration time, but by ID as well. And so the way to do that is we have a separate dictionary where the keys are the block IDs, and the elements are pointers to where those blocks are in this priority queue. So that's the way to augment your priority queue so that you can access not only the minimum element, but an arbitrary element. Yeah?
I'm saying it says the person, but how do you handle pointers and like that in Java?
I'm not sure exactly the way to do it in Java. I'll pull down an example and put it up on the website for details.
And I just remembered you box it up into an integer object, for instance.
Yeah, that should work. But so in general, you're going to have an augmenting dictionary that lets you access stuff in here independently of its properties as a heap. So now you can try and use that extra dictionary to go in and say, OK, we've got a heap here with elements with times and IDs. And then we've got a dictionary where we have an ID that points to a particular element in our heap. So one way that you can start by trying to do access requests. So when we access something, we need to update this time here to some new time based on when our access request came in. And so if you try and do those updates directly and change these while they're still in the heap, the problem is that you'll change it, but the heap will lose its ordering. It won't act as a real priority queue anymore because you've screwed up the organization by swapping numbers around. So if you had maybe something up here that had an access time of 1, something here that had an access time of 3, and something here that had an access time of 4, and you went in and said, OK, we just accessed this one. I'm going to update that to 6. Now, this isn't a valid heap anymore because the minimum isn't at the root. So you've got to do something else. So rather than do direct updates, what we're going to do, so suppose we need to modify this one. This starts out as 1, 2, and 3. And we have an access to this ID at time 6. So rather than go in and directly key on this element, what we're going to do is key on that element and mark it as useless. It's expired. We're not going to do anything with it anymore. And we're going to insert a new element with that ID down here. So that's going to be our 6. And now our pointer doesn't go here. That's expired. It's going to go down here. And so now we've got our properly organized priority queue. We've got our dictionary that still points to everything. And now when we do free requests, anytime we see something like this, we just pull it off and we throw it away. It's useless now. And so we'll pull that off. We'll promote our 2 here. And now when we look for the minimum time, this is going to be the correct minimum time rather than this one, which is what it was if we did direct updates. OK? So that's the complicated bit. That's how we would augment a priority queue to support these kinds of operations. All right? And congratulations to the people who correctly solved those optional problems, because it's not simple. All right, let's talk about our main topic today. So I said in the class outline I was going to talk about dynamic programming today. Who's done dynamic programming in their normal classes? Everybody? OK, so we've got a lot of people are going to be new to this then. All right, so I'll try and take some more time for the dynamic programming. So I am going to talk about it, but before I get to that directly, I'm going to cover some alternative approaches that you can also use and kind of compare and contrast them to each other. So I'm going to talk about 4 quite general approaches to problems that we can take to try and solve them. So the first one we're going to talk about, I first mentioned in the very first week of class. That's the complete search. That's kind of a crappy marker. So that's a complete search or brute force. And so we'll cover that in a little bit more detail. The second one is a binary search. And I talked about this a little bit in the context of bullseye, which was the first week's problem. Binary search. The third is a greedy solution to a problem, and this is related to a dynamic programming. And the fourth is dynamic programming. And so these will get more and more complicated as we go down. So we're going to start with the simplest one and kind of move up from there. So we talked about complete search already. What do we need a problem to have in order for a complete search solution to work? All right, so first thing we need is we need to be able to enumerate all possible solutions. Okay? So a comprehensive enumeration of every possible answer you could have to the problem. So maybe the answer is an integer between 1 and 10,000. Then you would have to be able to enumerate between 1 and 10,000. So maybe it's the answer is a permutation of 5 elements. Then you'd have to be able to loop through all of those possible permutations. Maybe it's a subset of 10 elements. You'd have to be able to construct all of those different subsets. But in some way, we have to be able to loop through every possible answer. Then you need a way to test whether an answer is correct. Okay? So in some way, you have to be able to say, here's a formula that tells me whether this answer is a good one or a bad one. Maybe you're looking for the minimum over all of the solutions. Then you would be able to loop through all the solutions and see which one of them is small. It gives you the smallest answer. But in some way, you have to be able to identify whether this solution works compared to all of the other ones. And once we've done that, once we've got these 2 steps, the way to construct a solution is very easy, or very straightforward anyway. We loop through every answer, we check and see if it's right, and if we find the right answer, we're done. Okay? Very straightforward, very simple, and there's only one problem. The other thing you need is a small, quote unquote small, number of answers. And that's because for a complete search solution to work, we have to go through every single possible answer and check it. And if there's a large number, that will be too slow. So what small means is going to depend on kind of the context of what you're working on and the problem itself. In the context of a programming competition, small means on the order of less than 10 million. So if you have fewer than 10 million possible answers, it's probably worth writing a complete search solution because that's likely to work in the time you've got allowed. So for something like, so if it's an integer, if it's an integer, positive integer, try it if the maximum integer is less than 10 million. If it is a permutation of some number of elements, means it can work if you don't have more than 10 elements because there are 10 factorial possible permutations and that's less than 10 million. If it's a subset of a larger set, it would work for a subset of less than 23. 2 to the 23rd is less than 10 million. But in general, you need some way not only to enumerate all of the solutions, but to count how many there are ahead of time to know whether a complete search method is feasible. Okay? So if you can use this method, it's usually a good idea because writing these kinds of solutions are a lot more likely to be correct than the more complicated ones. It's harder to get bugs in these. And they're also faster to write. So you'll save time that can be used on other problems. The other time when you might want to think about trying a complete search approach is if you really want to use something more complicated because the maximum limits are really bigger than is feasible, but you're having problems getting a correct answer with these more complicated methods. Then you might want to use a complete search solution on some smaller sets, get some correct answers that you can use as test cases for your more complicated solution. Okay?
I have a question.
Yes?
So what's the reason that you can't have this for like large number of things?
Because it will take too long. So if you have, say, a set of 100 things, and you're going to generate, and the answer is some permutation of those 100 things, how many possible permutations are there?
I guess
100 factorial, which is really big, and so there's no feasible way to go through each one of them independently.
I know the limit of like a small number of answers, but large number.
For a programming competition, 10 million is a good rule of thumb. So if you have less than 10 million, it's worth thinking about. Obviously, it's fuzzy, but that's kind of a good starting point. Okay, so this is complete search. Let's talk about binary search. So for a binary search, rather than being able to enumerate all the solutions, we need to be able to bound the correct solution. So maybe the answer is a positive integer. We need to have some upper and lower bounds on what that integer can be. So maybe we know that it's a positive integer and it's less than 20 million. Then our lower bound is 1, our upper bound is 20 million. Okay? That's what you need for a binary search to start off with, is a bound. And then you need to not only be able to test whether the answer is correct, but your test also needs to tell you, is the test answer greater than or less than the correct answer? All right, so if we do a trial test on some number, we want to get information not only whether that particular answer was the right one, but whether the real answer is less than or greater than the answer that we tried. Okay, so let's talk about an example for this. Let's take bullseye. We talked about that last week. That was the first week's homework. And we had worked out as part of our problem this solution for the total number of paint it takes for n rings. So let's assume that R here is 1 and T is 550. So this is our test case we're going to work through. Then that gives us a solution for paint in terms of n of n times 2n plus 1. Okay? So we worked out for the small case, which this is under the small limits, that n is less than or equal to 22. 22 was the maximum number of rings that we figured out that you could draw in that case. So we know that n is positive, so 1 is our lower bound, 22 is our upper bound. So we pick a number in the middle, say we pick 11, we can go through and calculate how much paint it takes to paint 11 rings, and that is 253. That number is less than how much paint we have. That means that not only do we know that it's not 11, we know that it's not any number less than 11, so we can exclude that whole section. We can remove half of the possible answers with one test. So then we go in, we do the next one, we check 16. And 16 is 528 is the answer. 528 is less than 550, so we can exclude this whole region. And we can keep doing that It only takes us 4 tests to find out that the correct answer is 16. So instead of having to go through each possible solution, like you would do with a complete search, you only have to do as many, you can do it in logarithmic time, because each step is removing not one solution from the possible answers, but half of them. All right? So this is the idea for binary search. This is a great approach anytime you've got this sort of, all the answers are lying on a number line, and you can exclude some part of the possible answers with each test. All right, so those are your basic approaches. And again, if you can use a complete search or a binary search, if those are feasible, they're great. You should use them. However, a lot of times they're not going to be. So let's talk about greedy solutions. Here's what you need for a greedy solution. First, you need what's called optimal substructure. What that means is that when you solve a problem, you can break that problem down into subproblems that look like it in some way. And that by correctly solving those subproblems, you can construct a correct answer to the larger problem. So let's talk about a problem. Has anyone done the coin counting problem before? This is kind of a classical one for greedy and dynamic programming solutions. All right. So this is coin counting problem. And the basic idea is we have some value A. Maybe A is, what did I pick A as? Let's pick A as 11. That's a good start. So we have 11 cents, and we have some set of coin denominations. So we'll have a penny, a nickel, a dime, and a quarter. And the question we want to answer is, what is the fewest number of coins we can use to generate this value? So if we start off with 11, we've got 4 technical options and 3 real options. We can start off by using a penny, a nickel, a dime, or a quarter, because we've got 4 possible coin denominations. So we can't do a quarter because we don't, a quarter is 25 cents is bigger than 11, that doesn't work. But we can start with a nickel, or start with a penny, leave with 10 cents. We could start with a nickel, leaving us with 5 cents or 6 cents, or we could start with a dime and leaving us with 1 cent. So that gives us, so we start off here, and then we've got 3 new subproblems. So this moving from the root to our next level takes 1 coin. So we spent 1 coin to get our number smaller. So now the correct answer is 1 plus the minimum of the solution to f of 10, f of 6, and f of 1. So f of 11 is that. So we can solve our original problem by solving these subproblems. Yeah?
Where did you get the 10, like after the 1 cent?
So here what we're doing is we're saying, okay, we're starting with 11 cents. We want to make change for 11 cents. So I'll take a penny, and now I need to make change for 10 cents. And same deal here. If I take a nickel, then I have 6 cents left that I need to make change for in some way. Does that make sense? Okay. So this problem exhibits optimal substructure. We have subproblems of the original problem. If we correctly solve those subproblems, we can correctly solve the original problem. All right? So how would you code a complete search solution to this? So a complete search solution would be, all right, at each step of the tree, these nodes branch. So we have 4 different options at each step. We can subtract, we can take a penny, we can take a dime, we can take a nickel, we can take a quarter. So they branch at each spot, and at some point, they reach these points where we can't go anymore. So we can find the optimal solution by finding the lowest depth in the tree where we've completely filled up our thing. And so we can do a complete search by completely constructing this tree. And so there are exponential number of nodes in the tree to first approximation because each node is splitting 4 ways. In order to solve this with a complete search solution, recursively, we would have to explore an exponential number of nodes. And that's going to be feasible for very small numbers, but it's rapidly going to get too slow as our sample size goes up. So what a greedy solution does is first you need optimal substructure, and then you say, OK, locally optimal choices lead to optimal solutions. And that needs to be true in order for a greedy solution to work. And then the way you do a greedy solution is at each step, you take the best option. So for this coin counting problem, the best step when we start with 11 cents is say, OK, we'll take the biggest coin we can. We'll take a dime from that. That's going to be our optimum. And we're not even going to evaluate these. We're just going to ignore them. We're going to assume that if we take the best step at each spot, we'll get the right answer. So here we've got a 10, and then we've got 1 cent left. So we can get the answer in 2 coins. And that is the best solution. And in fact, for this particular problem with this set of coins, greedy solutions work great. So you can have, as you know, if you've ever tried to make change, you take the biggest coin that you can with however much change you're trying to make, and that gets you the answer, and that gets you the correct amount of change in the fewest number of coins. All right. Proving that a greedy solution works is hard. Let's talk about a related problem. Same general outline, but we're going to change the denominations of coins we have. Going to have a 1 cent coin, a 3 cent coin, and a 4 cent coin. And let's look at a equals 6. So we start off with our problem at 6. That generates 3 different solutions. We're not going to evaluate the smaller ones because we can take our 4 cent coin and be left with 2 cents left. And then same deal, we're going to take a 1 cent coin and then another 1 cent coin. So we have 3 coins, right? Is that right? Somebody say yes or no. No, right. What's the correct answer? 2 3 cent coins, right? And that means that for this instance of the problem, a greedy solution doesn't work. You'll get the wrong answer. So how do we solve this without going through the entire tree? Well, let's take a look at the tree for a slightly larger problem. Let's look back at a equals 11 again with this new subset. So we've got at the root 11. That generates subproblems of 10, 8, and 7. Each of these generates 3 subproblems. Over here we've got 9, 7, and 6. Over here we've got 7, 5, and 4. And over here we've got 6, 4, and 3. So each step each subproblem is generating 3 new subproblems. So we start off with 1 problem, then we've got 3 subproblems, then we've got 9, then in the next row we'll get 27, and then so on and so big. So each one is a new power of 3. But if you look at this, you know, this is going to have a depth of about 7 or 8 levels, which means there's going to be 3 to the 7th subproblems. However, a lot of those subproblems repeat. So here's a 7, here's a 7, here's a 7. We're solving the same subproblem lots of times. The correct answer to a equals 7 is not going to change from when we evaluate it here to when we evaluate it here. So if we do the complete search solution where we're exhaustively analyzing every subproblem independently, we're repeating work over and over and over again. What's the total number of actual subproblems, independent subproblems there are? Can anyone answer? So if we don't look at independent, we know there's 3 to the power of whatever the depth is. But so we start off with 11. The subproblems are smaller than 11, and they're positive integers. There's only 11 actual independent subproblems. So rather than doing 3 to the 7th evaluations of these subproblems, if we do each subproblem only once, we can save a lot of work. Okay? And that is the basic idea of dynamic programming. And the technical term for that, so this is what you need for a greedy solution. For a dynamic solution, what you need is overlapping subproblems. And that means that the same subproblems show up in your complete tree multiple times. And so you can save a lot of your work by not solving them more than once. And so there's 2 standard ways that you can implement this. So suppose that you have a recursive algorithm that correctly solves this problem. Okay? Then one way to do it would be to say, okay, I've got my function f of a, and that works. That's great. So let's write a wrapper function. We'll call it g of a. So we'll say def g of a. We'll define a cache inside that function as an empty dictionary. And then every time this function gets called, if a is in the cache, so if we've already stored the solution to that subproblem, we're just going to pull it out of the dictionary. We'll return cache a. Otherwise, we actually go in and calculate it. And when we calculate it, we're going to put it into our cache for later use. And then we return it. And that means that every time we go in here, so the first time we hit this 7 subproblem, it's not in our cache. So we calculate it using the original function that we've done. And then we put it into the cache and we return it. And then the next time we hit it, we don't have to calculate it again. It's in the cache, we pull it out of the cache. And that's much faster than trying to resolve that subproblem. So this is called a memoization approach, or a top-down dynamic programming solution. The other way to do it is we know that there's only 11 possible subproblems. So let's make a list of all of them. So here's our subproblems 1 through 11. So we can start at one end. We can make a table of all of the solutions. So we'll allocate an array with 11 elements. We'll start off here at 1. The correct answer to 1 is you need 1 coin. You need a 1-cent coin. For 2, it's 2. For 3, it's 1. For 4, it's 1. And then for 5, we get here. 5, we've got 3 subproblems. We've got 5 minus 1 is 4. 5 minus 3 is 2. 5 minus 4 is 1. So it is 1 plus the minimum of the solutions to those. And we've calculated those already. The minimum is 1. So the answer to 5 is 2. And then we step through iteratively evaluating each position in our array. And then we have a table of all of the answers. And we just pull the correct answer off the end. All right? So this is going to be a very widely useful technique. You'll use this all the time, including in future classes, because I'm going to give you problems that require dynamic programming constantly. And you'll see it in programming competitions as well. So so the other thing that you can note about dynamic programming solutions. Suppose that we had this problem and S was fixed. So S was the same between different test cases. And we start off, but we're giving you maybe 50 different cases of A. So we start off with A equals 11, and then we do A equals 55, and then we do A equals 7. So we've got a list of a large number of different possible A's. You can use the same table between cases. Once you've calculated it for one answer, you don't have to go back and reevaluate it. You can save it. You can use memory to store it for later use. So once you've calculated this A equals 55, you should know the answers to all A's less than that. And this is just a cache lookup now. You don't have to do anything more than that. So that's another way to sort of save time between cases when you're doing these. All right. So I've decided to change the way we do lab section a little bit because I know most of you are not being able to get through the problems I've set during the lab. So what we're going to do this week is I'm going to have you start working on the homework problem during the lab section, and then you can ask me and the TAs for help, advice on the homework, and hopefully maybe spend a little more time or a little less time outside of class working on it, since I saw that a lot of you were spending more time than I really want you to spend on it. So,
How much time are you expected to spend?
I was expecting you to spend somewhere between 2 to 4 hours. And so I gave a poll on Piazza, and I saw that probably about a third of you are spending more than that. So I would like to make it a little easier for you to solve that in the time that I have in mind. So I'm gonna talk about that one sec. So take a look at the homework and go ahead and solve that, and I will be here for questions. It's going to be a dynamic programming problem. In addition, if you remember back when at the first week of class, I told you that in order to pass the class, you're required both to turn in some number of homeworks, and you're also going to have to compete in one programming competition that will hold as a part of the class. So the ACM is organizing a regional qualifier for the ICPC. So if you're interested in that, that will count as one of your practice competitions. So you can do that and not have to do one of the other ones we're scheduling. If you do want to compete in the ICPC as a part of one of the WashU teams, you do have to do that as well, because that's going to be required. That's how they're going to set up teams. And so Joey here is the one who's organizing that. So if you're interested, you can talk to him and ask him how to sign up for that. I believe you need to sign up by next Friday. Is there anything else you need to say about that?
Yeah, it'll be, the actual time is going to be 2 weeks from this Saturday. That is the 27th from 2 to 7 p.m.
Okay. And so if you can't make it, that's fine. We'll be scheduling other ones that will count towards your requirement for this class. But so if you are interested, talk to Joey and get set up for that. All right? So try out the homework.